I'm Ethan Campbell. I'm a PhD student at University of Washington, as is Katie Christensen here, and Katie and I will be running the Python tutorial. Um, Ryan Anderson and Rue Nicholson are here, and they will be monitoring Slack, both at UI, and hopefully monitoring the WebEx chat too. And if you have questions, feel free to put those in the WebEx chat or Slack. If it's more of a complicated technical question that's a bit longer, then maybe Slack is easier. But we'll be watching both of those. And before we start, just want to make super clear, so there's a little time in case you haven't done this already. If anyone does not have a personal Google account, so not an institutional one, like if you have one through your university, if you don't have a personal Google account, we are recommending that you use one of those for this tutorial. If you have an institutional Google account and you know it works with Colab and you've used it with the Google Drive integration with Colab, then great, awesome. If you're UW, you're fine. But we do recommend you have that. So it's quick to set up. Just go to google.com. So it's 11:06, and yeah, let's do this. So I think the place that we're going to start from is this GitHub link. So we're going to start at the Python repository, and this will be here after the tutorial is over, so you'll be able to access these resources later. And there are a few steps to get started. Pretty simple. We're going to just follow these one by one. I should mention, though, if you want to just follow along without actually coding, you can do that by clicking on this link and viewing a non-fully interactive view of the notebook that we'll be going through. So here's that link. You can just follow along, and you won't be able to play with the code, but that's a quick way if Colab is not working out for you. And for anyone who can't access Google, and I'm thinking here perhaps people in different countries outside of the US, if that's the issue, then you can always download this, the Python notebook, and run that locally. And if you need help with that, I'm sure there are folks who can assist here. So the very first step we're going to do is go to this first file, or you can click on the link here. GO-BGC workshop python tutorial.ipynb. This is a Python notebook, so it's a bit different than a script. And the next thing to do here is to click this Open in Colab button. And it's over here. So I have the instructions. And this is really nice in that GitHub integrates with Colab directly. So once you do that, you're going to access this view of the Python notebook. It should look familiar for anyone who's used them. But you'll notice that if you start trying to edit it, you can't save these changes. This is sort of just a read-only view. So the next step is going to be to click this copy to drive link. And what this is going to do is create a editable version saved in your Google Drive. And also, I should say, if you haven't logged into Google yet, you should probably do that. Choose that personal account. And when you click this link, it may open it in a new tab automatically, or you might have to click. But either way, you should get this new editable view, and I'll post in the Slack for Drew, who's just asking for the GitHub repo link. There we go. Okay, so now you should have this view. It should say copy of GO-BGC workshop Python tutorial. And this is the version that you're going to be working with that you can change. It won't modify the GitHub version, so this is all, you're free to do whatever you want in this notebook here. I should mention that this tutorial is geared towards newer users. So those of you who are more experienced with float data, some of this is going to be review. But our hope is that everyone will come away from today with something new. I think it should be a fun time here. So we've reached this point. Want to know if anyone is having trouble getting to this point. And if you are, you can use the chat in WebEx, or sort of these emoticon. There's some reactions somewhere in WebEx. Like a thumbs down.
The request to increase the font size to zoom in a little bit.
Yeah, definitely. Thanks, Nancy. Hopefully this is easier to read.
That's great.
Cool. Okay, so I'm seeing no issues with Colab. You're all at this point. That's good news. And what this has done is it's saved in your Google Drive a copy of the notebook in what should be the folder Google Colab. So, or Colab notebooks. Okay. And it should be there. You can move it in or out of that folder into a different place if you'd like. How do you get to the notebook and Colab? Um, so that's starting from the GitHub link, following those instructions in the repository that was linked over here. I'll put that link again. Clicking on the notebook file, clicking open in Colab, and then clicking copy to Google Drive. Eric, let us know if you have any issues with that. Okay. So I think hearing no other issues, I think we're good to move on, and I'll hand it over to Katie for this next section.
Great. So now that everyone hopefully has a copy of this notebook primed and ready to go, we're going to talk about getting it primed in our Google Drive and setting up everything to actually run through our code. So this is going to be entering into the Python programming world, and we're going to open up that first setup bit, the drop-down menu there, and you can hit the little caret next to it there, and that'll help us move along. All the sections are then numbered in that way, and we're just going to move through the different sections. So at the very top, we have some information about this general workshop, just underneath the GO-BGC workshop title there. If you have any questions, like we said, put them in the chat. That's happened quite a bit, so thank you guys. People who created this, we did all the introductions, and then attribution. So we're using GO-BGC data for this and SOCOM data for this tutorial. We ask that if you use these things in your research, please acknowledge them and do all of the proper acknowledgements. You don't have to acknowledge this code with formal attribution, but we want you to link to our GitHub so that other people can find what you're doing and get cool research out of it. So now getting set up for our Google Colab. The reason we're using this is because it's free, cloud-based, so we're not running anything on people's computers. It makes it easier to translate between machines, and it's a Jupyter Notebook platform, which is pretty easily human readable. Couple of how-tos on this. These cells are either text or code. The code, you can see it's kind of in the little gray boxes, and then the text, you can see Ethan is clicking through that. And you just can run these by hitting Shift-Enter or Shift-Return, or there's usually a little play icon on the left top corner of the cell, and you can run your code in that way. If something isn't working, if it's for some reason breaking down, you can restart your runtime in the runtime drop-down menu on the top there. And you can see there's a restart runtime, which since we haven't run anything yet, you can't restart it, but as soon as you do, you can restart it in order to make things work better for you. Hopefully that's clear for everyone. You can play around with it a little bit. It's very similar to Jupyter Notebooks if you've worked with that format at all. So let's go ahead and actually run our first cell here. The first time we run this cell, we're going to be asked to navigate to a link. You're going to click on the link, and what this is doing is giving it access to your Google Drive. So that means you can put data files, open up new folders, and that kind of thing in your Google Colab notebook. So you can go ahead and step through clicking on our link, and you're going to have to select your account. This is why we suggest you have a personal account. It just allows that access. So signing in. And you're going to copy this link in order to put it in as an authorization code. We're going to take a minute here. I want everyone to give me a thumbs up reaction or put in the chat if you're having issues. And hopefully this is going to be working out for everybody here. Great, seeing lots of thumbs up. That's good. Yeah, so at the very end here, you should see mounted at /content/drive, and that should be now primed into your Google folder. Google Drive and able to access those things. Yes, you can see all of Ethan's lovely folders. All right, so now that we've accessed our Google Drive, we're gonna actually start loading things into Python and sort of opening up our important packages and getting some of the coding stuff ready to actually read our data. So we're gonna run this cell. It's got all of our import statements, and there are a couple packages that aren't in the default packaging of Colab. So we have to do a pip install with the exclamation point on that top there. And that just gets us those packages into Colab so that we can use them. And then we have all of our import statements. And then finally, we have a bit of code that will now open up and create new files on your Google Drive. So this file will be called GO-BGC Workshop. And inside of that, there will be two other directories called Profiles and North Atlantic. And that's where we're going to be putting the data that we're using in our workshop today. So hopefully everyone can run through this and there are no issues with the import statements. In Python, we need these packages in order to use the tools that they have in them. So great. If anyone is having issues, speak out now in the chat or with a thumbs down reaction. Otherwise, I think we are going to move along to the actual functions to download our float data.
Super. Okay, so we are on part 2 here, and I'm going to unhide the cells. Thanks, Katie, for stepping through that. So we are all set to start coding, and what we've done here are write 2 functions that we think are broadly useful. We won't go through all the code in this. You're free to borrow these for your own research. The first is called download file, and it basically just downloads and saves a file from any given URL. It has some options you can select where it's going to download to, that's save to, whether it's going to overwrite existing files, and whether it's going to tell you what it's doing. And this uses the requests library in Python to download files. And it's not the most resilient code, but it does have a bit of error handling in case the download doesn't work well. Now, the second function here is called argo GDAC. And this uses the GDAC index file that you heard about from Allison and earlier on Monday from Tanya. And the GDAC index file, again, is this in either the US GODE or the Coriolis GDAC. It's this synthetic profile index.txt file. And it has an index of every single float profile that you could possibly download, as well as some metadata. So what the function does is it downloads that index file, which is about 30 megabytes, and then it uses some criteria that you specify to choose certain float profiles. They can be geographic criteria, Latin long, start date, end date, particular sensors that you want to make sure the float has, or specific floats if you already know the WMO IDs of those floats. Again, you can step through this on your own time if you're curious. There's a bit of documentation about how to specify these arguments. So this is some versatile code that we hope will be useful for everyone. And then at the very end of this, if it does download files, it returns a few variables. It returns the WMO IDs that were downloaded. It returns a view of that index file that has been subsetted. And then it returns a list of the file names that were just downloaded. So what we're going to do is go back up to this first cell, the download file cell. You can run it again by clicking the play button or by going Shift-Enter on your keyboard, or Shift-Return. And all that does is it's loading this function into the namespace of Python so you can access it later. So nothing really seems like it's happening, but you're just running that code to load the function. And let's see. I think one, would the function work with core Argo stuff? We have a question in the chat. It would with a very small number of modifications. You'd have to change the file name and just make sure that the columns all match up. But yeah, it's it should be helpful there. I think that's it for the section. So we're gonna hide this and move on to 3.
Yeah, so great. Now that we have those functions, let's go ahead and actually do an example case of using the functions. And we're going to give the example where we know the single float that we want to load. So we're going to say we know the float's WMOID, which we're going to be using float number 5904183. And we're going to plug that into our Argo GDAC function. So we're not going to bother with the latitude, longitude, start and end date. We know the float number, so we can just put that as our argument. Everything else can be none for the narrowing it down. So if you go ahead and run this, like Ethan said, it will give you 3 outputs. It will give you the WMOID, which in this case is exactly the number I read off. It will give you the GDAC index, or no, sorry, it will give you the downloaded file name, which is, of course, the float number and the sprof.nc, and that's the format that it's in the GDAC on. And then it does give you the GDAC index heading, which here we can see the first 3 lines we printed out at the very end here. You can see that it's got the file, the date, the latitude, the longitude, that these profiles, which these are the individual profiles, you can see that it's the 001.nc, 002, 003, and those are the individual profiles in the GDAC index file. So we've actually loaded the data from this float, and it should be saved into your Google Drive.
It should. And we have a question in the chat from Joan. I got name error. Name Argo GDAC is not defined, and that means you probably haven't run that cell of code up here in section 2 to actually load that function into your namespace. So just run these 2 cells here.
You have to run both the cells. You can't just run the first one.
Yeah, there are 2 cells. These 2.
Is anyone else facing an issue with loading this, or has everyone managed to get their WMOID, download file names, and GDAC index things to work nicely? Lots of thumbs up. That's great.
Okay, good. Why are there 3 NC files?
Yeah, so those 3 NC files are for the individual profiles, whereas the full sprof file is all of those compiled together. So you can see here that it says AOML 5904183/profiles/SD, the same number, 001, and then 002, 003. And that's just the first profile, the second profile, the third profile. The actual S profile is going to be in AOML 5904183/ the file name, which is the downloaded file names output that we got from our function.
Yeah, so you'll see it in Google Drive in that GO-BGC workshop directory that was created. You should have now the single sprof file. And yeah, we do find that easier to work with than the individual profiles. Okay.
Yeah, the individual profiles are nice if you are looking in just a specific geographic area and you don't care about what float number it is, but you want everything just from that little area. So you can select out the individual profiles and maybe not worry about the float number, but in general, it's best to keep them together and whole.
Mm-hmm.
All right, I think we're going to move on to our
part 4, yeah. So part 4 is loading this netcdf file that you downloaded. And let's unhide those cells now. And the package we're going to use, as I think we hinted in some of the email communications ahead of this, is the Xarray package. And Xarray is really the gold standard today for loading netcdf files into Python. There have been other ways to do it, but most people use Xarray now, and it's so easy. The function that Xarray has to do that is called open dataset. And we're going to do that in a single line by saying XR, which is the shortcut for Xarray, sort of like NP is the shortcut for NumPy. Open dataset, and here's your directory path that was set in the very, I think, second cell. And downloaded file names, ~0 is just using the first item in that list of the downloaded file names. And we're saving that Xarray object into the variable called data. Okay, so the second line, don't have to worry about this too much, but we're just swapping some dimensions, setting the cycle numbers as a coordinate to make that easy to use. And then the way that you view an Xarray data set is just by using this display function. You can also just type data, I guess, at the end of the cell, but display data is most clear. So let's run this code. And what we get is this really nice interactive view here. And we just put in a nice little comment in the chat there about the file structure. So let's see, what we can learn from this is that to start on this very first line, X-ray tells us the dimensions. We know that there are 7 parameters, that's n param here. There are 233 profiles in terms of profile numbers. And then the maximum number of levels in this data are 557. Okay. And for each of these variables, if you click on this data variables pane, this opens up here. I'm going to zoom out a little just so we can see more. There are 78, so there's a lot of data in here. And you can view the metadata for each of these variables by clicking on the little page icon on the right that pops open the, say, the long name, dimensions, and you can actually view the data in some cases by clicking on this cylinder icon on the right. So it gives you a window into what the data look like. So I think we have a few sort of interactive questions just to get people's brains working and fingers typing. And the first one is, if you were to look at the profile number dimension and the profile number coordinate, these are different things here. How many profiles are included in the data file? We put this in the WebEx chat. And then how many profiles have actually been collected by the float? And these are 2 different numbers, and this is sort of an exercise to explore the pane here. So anyone can feel free to answer those 2. Number of profiles versus the number of profiles in the data set versus the total that have been collected by the float. Yeah, Nancy, 233 profiles, 244 in the data set. And how do we know that? It's because profile num is 233. And if you look over here at the coordinate array, you can see it starts at 1, it goes up to 244. So while there are only 233 provided, the float has actually taken 244 profiles in total. We just don't have all of them in this data. For various reasons, it could be, I think in this case, the float is at the end of its life and it didn't manage to transmit all of its data. Okay, next question. Exploring some of these variables, what are the units and long name of the variable BBP 700? Anyone but Nancy can answer this one. Derek asks, has the SPROF merged the BD and the SD data from all the individual profiles? Not familiar with BD. Maybe someone else can answer. Yeah, wow, we have great answers from Pirseb, from Drew, and from Joel. It is indeed backscattering coefficient at 700 nanometers, and we know that because if we scroll down to BBP 700 and we look at the long name in this little attributes pane here, we can find that. It also gives you the units and some other metadata, including the resolution. And you can see how many values there are, 100,000 values there. That's great. Okay. And since I think we took a little time, I'm just going to answer this next one. On what date was this data file created? If you scroll down to the very bottom, you can see metadata that apply for the entire file, right? And that's in the history. You can see the creation date. It was created on May 14th, and you can see the version of the Argo data that this is. Just a little comment about the structure. You'll see at the top there are a lot of sort of forms of metadata and the dates, latitude, longitudes that have dimensions of time, profile numbers here. And then at the bottom, you'll see that there are grouped in sets of 5 or 6. These are the actual variables, so pressure, temperature, salinity, oxygen, etc., that are measured. And you'll see that, for instance, there's temperature QC, temperature depress, which is the displacement from the actual sample value, is usually a small value because this is a merged profile. Temp adjusted QC, or a temp adjusted, and then temp adjusted QC here. and then temp adjusted error. So for each of these, there are different variables that we'll find useful. Okay. So I think this last part of section 4 here, we're just going to use this data and very quickly using Xarray's magic plotting library to create a quick scatter plot of longitude versus latitude. So this is where the float has profiled. So we're doing dot scatter, longitude, latitude. You don't need to know the syntax. It's just a shortcut. And we're coloring it by position QC. So if you run the cell, you'll see that we get two different colors where position QC, meaning good positions, are blue, they're 1. And then QC flags of 8 for position, which indicates positions have been estimated by interpolation. Those are orange. And you can see very clearly this float was from the Southern Ocean. It lasted 6 or 7 winters, and each time it went under sea ice in the winter, those profiles positions have been estimated by interpolation because we don't have real fixes for them. So that's what's shown here, and we're going to move on to section 5 now.
Okay, so let's go ahead and talk about the date-time integration, which is actually this is a nice section because Xarray does a lot of it for us. So let's take a look at the timestamps of our float here, and we can do that by accessing the file that we've loaded in by saying data, square brackets, and then Julian days, JULD. And you can see it prints out this Xarray data array with quite a bit of metadata. And you can see in the numbers, the data type is this date time 64. Sometimes we don't want all of that metadata and that extra stuff. We just want the numbers. So we can access that using the dot values function on our data accessing Julian days. So in the quotes, JULD dot values. And if we print out the first 10 of those, you can see it gives us just the numbers, none of the extra metadata. But if we check the type, it is still a NumPy date time 64. So it still plays nicely in the dates that Python has set up. So you don't have to do a lot of formatting in order to make that nice. We can access any other data variable, or in this case, we can access the profile numbers using the same formatting, the square brackets and the quotes, and then you can say dot values to just get the numbers. And we can do the exact same test that Nancy gave us the answer to before, checking the number of profiles that have been sent to us versus the number of profiles that have been taken. So you can do that using the length function, len, of the profile numbers, which is what we just read in. You can see there are 233 of them. And then you can check the actual numbers by using indexing. In this case, we've indexed -1, which is just the very last item in the list, which is 244. So you can see there are 11 profiles missing somewhere. And if we plot that with our time, so in the next cell, we have our scatter plot with our profile numbers on the x-axis, our timestamps on the y-axis, and a couple of other formattings with the color and the size of the dots. And we have our X and Y labels, and you can see at the very end is where we start missing those last 11 profiles. And as Ethan said, it might be because it's the end of the float life. It might be because it hasn't gotten transmitted past being in ice for any number of reasons. So that's how you can access into the data that we read in and sort of start to play around with those numbers without having to carry all of the extra metadata using that dot values. So now that we've gotten that, we can move on to other variables, like in number 6.
Super. Okay. So we're going to look at pressure because it's you have to use it to interpret really any of the other variables. And I just want to make the point that as you've heard from others, I think it's particularly Tanya on Monday, we should always be using the adjusted versions of data. I don't think pressure gets adjusted often, but in general, it's best practice to use the underscore adjusted versions. So we're going to view that in its Xarray format, so we're not doing dot values here. And it tells you that there are 557 depth levels. Now, since this is a synthetic profile, that means that not every vertical profile in time necessarily has 557 depth levels. That's really just the most possible in this file. And if we look at the attributes, you can find that pressure is in decibars. I think that's what this is showing. So if you wanted to, for instance, extract the units for, to use in a plot label or something, you can use this .attrs syntax. It gives you back a Python dictionary, and you can access that pretty easily. So going back to that important point about the 557 depth levels. So if you look at dot values here, you can see the structure of pressure is a 2D array. And going vertically here, this is going in time. So this very first line is the first profile. If you look at the end of these profiles, you can see that they end in nan values. Nan is not a number. And this is essentially padding to make these all a uniform length, even though they all have different numbers of actual values listed. So for instance, this profile here has 3 nan values at the end. And this gets to the challenge of working with sprof files that we have to deal with, and that each of the profiles are sampled at different points, and that they're different lengths. So we're going to use indexing to index into that this 2D array structure and get out that first profile. And there are 2 ways to do this. In Xarray, if you watched that sort of tutorial video before this, you'll know about the .icel notation, or if you're familiar with Xarray, you can do .icel prof_num equals 0. You can also just use standard Python brackets indexing, which is a bit less clear what's happening, but that gives you the same thing. So we're saving that into this variable called first profile pressure. And these do the same exact thing, these 2 lines. We're going to examine the first 10 and the last 10 pressure levels. Again, we can do that using the display function for Xarray. And you can see that the pressure for this profile starts at around 5 decibars. It ends around 1599 decibars, so about 1600 meters. And again, you can see the padding at the end. One thing to notice is that the sampling is a lot more frequent at the surface, the sampling interval, and then at depth, it's about every 100 meters. So that's something to keep in mind, that the sampling pattern changes at around 1,000 meters for floats. Okay, I think we're gonna move on to 7 now. And if there are any questions in the chat, feel free to just put those in and can try to answer those.
Yeah, so just like every profile doesn't have all of the pressures, every sensor doesn't measure at every single pressure either. So we're going to sort of dig into that. We're going to look at the salinity, which accessing again in the same way that Ethan said above, with the dot values bracket 0. So accessing it using the sort of NumPy array instead of the Xarray icel type format. So if we display that, you can see that it is very full, right? Every, for at least the first 50, every single pressure measurement has a salinity measurement to go with it. If we look at the exact same access of the nitrate, and remember, we're using the adjusted data for both of these, you can see there are lots of nans filling in all of this. And that's just because the nitrate isn't measured at every pressure level. It's measured, it looks like every third at the beginning roughly, and then sort of moves on to a few different levels. So keep that in mind. It's not always going to be completely filled in with all of the different sensors, and you might have to deal with some sparseness, which we will talk about in the next section if Ethan is still there. I think your video disappeared.
Uh-oh. Maybe start that. Is the screen still showing though?
Your screen is still good. Yeah.
Good. Okay. Just restart a video. Hopefully that's working. But it's okay if it isn't. Well, let's move on to section 8, plotting a vertical profile. And thanks for sticking with us for all that, all the stuff above that wasn't the most exciting, but I think this is where it gets more interesting. So what we're going to do is use the Matplotlib library to create a simple line plot of your nitrate values versus your pressure values. And we quickly see that there's a problem here, and that the deep values are showing up, but the near surface values are not. And Andy has a really important point in the chat there. R means the file only contains the raw data. D means that it contains both raw and adjusted data. Yes, and B is BGC, S is synthetic. Yeah, the nomenclature is so important there. And I'm guessing you all can figure out what's going on here, but just to make this more clear, if we use scatter instead of plot, so we're plotting just the individual points that aren't connected, we get the profile, the full one, like we're supposed to. So what's happening here? It's that sparseness, the fact that there's a lot of NaN padding, and the NaN values are not being connected by matplotlib. So what we have to do now is mask out to extract out the good values and leave behind the NaN values. And we do that using NumPy's isNaN function. So that creates an array of Booleans, so true or false, where true represents NaN values, false is actual data. And we're going to save that as this variable called mask invalid levels, some descriptive variable names here. And we're going to then invert that using the tilde symbol, so true is now going to be the data we want. And what you can do with a Boolean mask is use Python brackets indexing to extract out certain index values. And we're going to index into first profile nitrate using the mask we created. And what we find is that the NaN values are ignored, which is what we hoped. And now we have all the valid nitrate values from the surface to the deep. And there are a lot fewer of them because nitrate is not sampled as frequently as salinity. And there are no NaN values. So that's great. We can now plot the entire profile as we were hoping. And we're going to do what we just showed here in these 3 steps, all in a single line of code. So I'm going to do first profile nitrate, brackets, tilde to invert that Boolean array, np.isNaN, and then the original nitrate values. So hopefully it's clear what's happening here, and what we get after extracting out only the good data is the line plot that we would like. So this is kind of cumbersome, but it is something you have to do when you work with sprof data, and when you're working with BGC data that's sampled sparsely. Okay, and I think we're moving on to section 9 now.
Yeah, so another thing you have to do when working with any kind of Argo data is checking the QC flags and making sure that you're using the adjusted fields. In this section here, there should be a table, but if it's not showing up, as you can see, Ethan's isn't. You can follow it at the link that is right there. And that just
happens
outlines,
if you're in Safari. If you're in Chrome, it should be fine.
And that just outlines the different quality control flags and what they mean, especially between the real-time and the delayed mode versions. And remember, delayed mode is, it's been gone through all of the system and been corrected, hopefully, if it needed it. And then the real-time is, it's just gone through the base automated level of quality control, but it hasn't, gone through the whole process yet. So in general, it's best to use 1s or 2s. 0s is no QC has been performed. You can use it, but use it at your own peril. 3s, 4s. The further down you get, the less likely you should be using it. That's an oversimplification, but for our purposes, we're going to be going with that. So let's just take a look and sort of visualize why we should be using these adjusted values and looking at the quality control in order to check these things. So we're going to access the nitrate quality control and the adjusted as well as the values of these things. And we're also going to access the times and the levels that these were taken so that we can get a nice picture over the life of the flow. So we're going to create these subplots we're going to create these subplots of the pressure and the time for each of the parameters. So the nitrate adjusted, the nitrate quality control flags, and then the nitrate adjusted quality control flags. So those are all of the different variable names that we're going to be digging into. And just like always, we are going to be doing that with the square brackets and then the quotes around the variable names. And we're going to be plotting them as lines. And if Ethan, you scroll down a bit, you can see sort of these 4 panels that we created with all of the different values here. So you can see in the very top left, this is the nitrate parameter. So these are the numbers that were given back. and they're not the adjusted values. And you can see that there are a number of values that are probably not so good. A bunch of it looks like pretty close to 0, or maybe even negative, right? In the middle there. And you can see if you look at the QC flags, those are flagged as 4s. That's the purple color in there. And the other ones are flagged sort of green, which in this case is 3s, right? So 4s and 3s, and those are just for the non-adjusted values. If you then go and look at the adjusted values, it's dropped out all of those, bad ones. They are marked with 4s, which if you go to your table, a 4 is data that have failed one or more quality control tests, or bad data that is not adjustable. So if it's not adjustable and you can't fix it, we're not going to be using it. And you can see here that now the QC flags have changed to be 1s, where the data is now marked, now being plotted in the nitrate adjusted. So going through my list of things, and yeah, so it's a double lesson here. Use the adjusted values. Make sure that you aren't trying to plot data that can't be adjusted and it's just residual. In order for if you want to look at the residual stuff and try and fix it, great. But it's a hard process. And then the other lesson is to always check your QC flags. Make sure that you're trying to use flags that are appropriate for your work. And for most scientific work, that's going to be a 1 or a 2.
Mhm.
So.
Thanks. And there's a great discussion in the chat there. Definitely, the comment from Annie is good. We aren't going to be showing the adjusted error variable, but that's a good one to reference. And I think what Nancy was showing here or mentioning is that even in the adjusted QC flags, you can see a mix of flags. You can see that the more recent data has probably only gone through the automated QC check, and therefore instead of this was probably good data here being flagged as a 1, it's still flagged as a 3, which is bad data but potentially correctable. And why is it bad data? Well, if you look at the difference between the nitrate and the nitrate adjusted fields, you can see that there actually is a difference in the values themselves. These are on the same color bar. So there has been some offset or gain correction applied, and the values themselves are different after this correction. So you do want to be using the
it's
the
also
adjusted.
possible that is hasn't gone through the full process yet, right? It's only been a few months since that time period, so it may not have gone through the full process and gone through all of the quality control corrections. I believe it's supposed to be about 6 months, right? For the real time to delayed mode. I think it's getting faster all the time, and people are always working on it. But yeah, the later you get in a float's lifetime to our current time, the more likely you're going to be running into the real-time data as well.
Mm-hmm. Yeah, a really good question from Pierce Sub in the chat. Do we ignore those 3s? It all depends on what your purpose is. If you're assimilating this into an operational model where you really need good nitrate data, maybe you don't want to use data that hasn't been checked, but you need to because it's you need the most current data. Maybe for research purposes, you might not use that, but it is totally up to you. And I should say Andy here is our QC expert with the GDEC. So all of our answers here are really good ones. Can the QC flag be empty after the adjustment? I don't think I've seen an empty QC flag. Purple, yeah, there's in the chart here that QC flag 9 is missing values, but yeah.
The values may be missing, but the flag should never be.
Yeah, this is I think the big thing that a lot of people miss when they're starting to use Argo or BGC Argo data, and they you're really excited about your research and you don't look at the flags, and then you end up using data that potentially has a drift or a bias, and or it's potentially just really bad. So always look at the QC flags. So we're going to move on to section 10 here. Is all real-time data marked at 3 or worse? Yes, for BGC data. Okay, interpolating. So again, there's some code here that we're not going to totally dive into, but you're free to look at what's happening after the fact, and to use this code in your own research. This is not research quality code. It's not perfect. It will not handle every edge case, but it does get the job done for what we're trying to do here. So as you saw that when we used Matplotlib's pcolor, it was just plotting the depth levels that were sampled. So if we want to interpolate that to create a more smooth, usable, nicer looking time depth section, we have to interpolate to a regular coordinate in pressure. And we're going to do that using SciPy's interpolate .grid data function. And we've created a simple function to do that, or actually a few functions. The first two it converts between, these convert between date-time format to float, which is necessary for interpolation, because SciPy can't handle date times. And then this next function is a bit longer, and it uses that grid data function to interpolate. And basically what's happening here is you're creating a new grid using the existing times and then a regular pressure axis, and meshing that to a 2D grid. And then there's a little code to specify only certain QC flags. So if you want to exclude, for instance, QC flag 3, you can do that by using this, the arguments in this function. And then it outputs the gridded parameters as well as the coordinates. Okay, so this is a really quick overview. Since we're short on time, we're just going to go down to what that looks like. So if we run this code, we're interpolating dissolved oxygen. And this is not the adjusted. We're doing, oops. So you have to run this code to actually save the functions. Okay. If you run this, we're doing exactly what we said not to do, which is to use the non-adjusted data. But you can see here, it's great, it's pretty, but there is very clearly a bad dissolved oxygen profile. Okay, so this is interpolated. These are just the upper ocean depths from 250 above. Here we're doing the same thing. That function can also take in the QC flags and interpolate those. So this is doxy QC, and we see that indeed there's that bad profile. It's flagged as 4, but there's also one that we wouldn't have really noticed looking at this. It's really not obvious that that's bad data, but it's flagged here using that QC flag. So it's really, really important to use this. Here is doing what we were supposed to do, which is using the adjusted version. Same code, going to run that, and you can see in the adjusted parameters that bad data is masked out, or it's gone. We've also specified using that argument function we created, specify QC flags to only use one QC flag 1. But if we didn't do that, it would have looked the same. So here's sort of what we're expecting, all good data. And just to show that you can do that with any other parameter, we're doing that with temperature here. You get a nice plot of temperature. The adjusted version, you can tinker with this and change this param name variable here into, for instance, psal for salinity or nitrate for nitrate, and rerun this code and have some fun with that just to see what those look like. But I think at this point we're going to move on to section 11.
Yeah, so this is our last section here. And now we're going to be looking at more GO-BGC data. This past float we've been using as an example is actually from SOCOM, which is great. But let's look at GO-BGC because this is what the workshop is for. So what we're going to do is we're going to download the data from multiple floats using our same function as before, our argo GDAC function. And instead of giving it just the float numbers, we're going to give it our latitude range, longitude range, our start date, our end date, and then the pH sensor, which is a very telling picture of that it's a GO-BGC float. And what this should do is select all of the GO-BGC floats in the North Atlantic. Yep, Ethan's got a lovely map there. So if you go ahead and run this, it should then put all of these files into the folder that we created on your Google Drives. And they should be named with the float number and sprof.nc. You can see that it's now loading multiple files, whereas before it was just loading the single file, and that's just because of the different arguments we put into this function here. So Hopefully that runs for everyone. If there are issues, go ahead and toss that in the chat and we can try and diagnose it. But from those files that we've just loaded, we're going to actually put them into an interactive map using Plotly. It has been created by Ryan. And Ryan, if you have things that you want to say about how this was created / what to look at, go for it.
This is actually really straightforward. So we're looking at, we're using Plotly here, which is a nice interactive plotting tool. So you can actually click around and scroll all over the map. It is just pulling out the data from all those profiles that we're looking at. So we're not looking at the directory data here. It's just all pulled from the metadata. So Ethan here can kind of show that you can click on things and zoom on things. It also has some hover attributes, so you can scroll over data points and see some of the attributes of those things. And that's all fully customizable. So if you wanted to create a plot with your own information or different data, you can do that. And one other note, since we're really low on time here, is that the base map you can also customize. So this is pulling from Mapbox, but if you want, you can go into Mapbox Studio, create your own account, and really customize your base map if you're looking for something fancy. So there you go. Broad overview on that.
So our hope is that you can use this code in your own work and adapt it as you will. We've hopefully given you a handful of tools that you can use, Plotly, Xarray, all those things. Hopefully helpful for you. And I guess it's a couple minutes until everyone, so I can take questions, comment on ArgoPy. It'd be in the works, and functionality will sort of overwrite a lot of things we've done here. Until that time, I think this will hopefully get us by. This is, as Ethan said, not like research code. It's code that you can use and adapt for your research. So
yeah, ArgoPy is great. They're doing fantastic work, and they're in the process of making it compatible with BGC data. So hopefully that will be a unique, a useful tool at some point. Yep. And for this function, you can play around and you can change the parameters just to check out the different data that our really brand new GO-BGC array has been sending back over the past year. So thank you all. We'll be around and able to answer questions on Slack if you have any, as well as in the coming weeks if you start using this data. Happy to answer questions too and help out. And I think I'm going to answer any questions in the chat rather than out loud here and in the screen share. But thank you all for participating in this.